folks, welcome back to another video on Advanced Higher Physics past papers, and this time it's the turn of uniform electric and magnetic fields. So as usual, we're going to the Calder Glen High School Advanced Higher Physics web page, then we're going to click on past papers, and then the first link you see there is Mr. Davies' interactive PDF of Advanced Higher Physics past papers by key area, and if you click on that, then an interactive PDF opens up and you just click on the question you want. And in this video then we're looking at fields, but we're going to look at uniform fields, and in particular we're going to have a look at 2019 question 15 and then 2022 question 14. And as usual, make sure you have a go at the questions first and then come back when you're ready and we will show you how we have worked through them. So firstly then, 2019 question 15. A small thin rectangular metal plate is connected to a DC power supply as shown in figure 15a, and electrons move through the plate from left to right, and a uniform magnetic field is now applied at right angles to the plate, and this is shown in figure 15b. And as electrons enter the metal plate, they experience a force due to the magnetic field, and this causes the electrons to initially follow a curved path downwards and gather at the bottom of the metal plate. And in part A, we have to determine whether the direction of the magnetic field is into the page or out of the page. Well, let's zoom in on that wee diagram, because we're told that the electrons follow a curved path downwards towards the bottom of the plate. So the bottom of the plate is going to become negatively charged, and if we want the direction of the magnetic field, then we can go back to our higher physics here and use our right hand rule. And if you remember, the right hand rule shows you the effect on a negative charge. Your first finger shows you the direction of the field, your second finger or middle finger shows you the direction of the movement of the charges, and your thumb shows you the direction of the force. So if you turn your right hand upside down so that your middle finger's pointing to the right, your thumb is pointing downwards because that's the direction of the force on the charges, then your first finger is pointing into the page. The direction of the magnetic field must be into the page. That's really a higher physics question. 15b, after a short time, the bottom of the plate becomes negatively charged relative to the top of the plate as shown in figure 15c. And this causes a uniform electric field between the top and bottom of the metal plate. Electrons moving at a fixed speed Vd, called the drift velocity, will now travel horizontally across the plate, and these electrons do not move vertically as the electric and magnetic forces acting on them are balanced. And in part 1, we have to show that the drift velocity is given by the relationship V subscript d is equal to big V, that's the voltage, divided by BD, where V is the potential difference between the top and bottom of the plate, B is the magnetic induction, and D is the height of the metal plate. Well, we're told that the electrons are now travelling horizontally across the plate, so the force on the charges due to the magnetic field must be balanced with the force on the charges due to the electric field that's been built up due to that potential difference. And from your relationship sheet, the magnetic force is equal to QVB and the electric force is equal to QE. And if you cancel the Q's, you're left with V equals E over B, where E is the electric field and B is the magnetic field. And again from your relationship sheet, the electric field strength is equal to the potential difference divided by the distance. Now that distance is usually the distance between two parallel plates in an electric field, but in this case it's the height of the plates. So we get V equals V over B times D, and that was what we were required to show. And just to be sure, make sure that you put the little subscript D in as well, and that it's a small v for drift velocity and a capital V for the potential difference. It's a short question. Okay, 15b part 2. The metal plate has a height of 3.25 times 10 to the minus 2 metres. The magnetic induction is 1.25 Tesla, and the potential difference between the top of the plate and the bottom of the plate is 3.47 times 10 to the minus 6 volts, and we have to calculate the drift velocity of the electrons moving across the plate. Well, that's just a case of putting those numbers into the relationship that we were asked to show in the previous part of the question. So let's write that relationship again. V subscript d equals capital V over BD. And then let's substitute the numbers in. So the potential difference was 3.47 times 10 to the minus 6 divided by 1.25 times 3.25 times 10 to the minus 2. And if you do that correctly on your calculator, you'll get an answer of 8.54 times 10 to the minus 5 meters per second. Electrons drift very slowly through electrical circuits, but that's a story for another day. Anyway, part 3, the magnetic induction is now increased, and the drift velocity of the electrons moving through the metal plate remains the same. We have to explain why the drift velocity does not change. Well, let's see if we can answer this by looking at the relationship again. So the drift velocity is equal to the potential difference over the magnetic induction times the height of the plates. And we're told the drift velocity doesn't change, it stays the same. And the height of the plates will stay the same as well. But we're told in the question that the magnetic induction is now increased. So therefore, for the drift velocity to stay the same, then the potential difference must increase as well. Now, why does the potential difference increase? Well, the increased magnetic induction is going to cause a greater number of electrons to gather at the bottom of the plate, and therefore the potential difference across the plate will increase. Or another way of looking at that is to say that the drift velocity is the ratio of the electric field strength to the magnetic induction. So if the magnetic induction increases, then the electric field strength increases as well, so that we get the same value for our drift velocity. That's pretty tricky. Let's have a look at the marking instructions. So part A was our right-hand rule that gave us the magnetic field into the page. Part B was the show question, where you get 1 mark for stating the electric force equation and the magnetic force equation, and the second mark for equating them. And then the third mark is for cancelling out the charge and rearranging it for the drift velocity. Part 2 was substituting all the values in to get your answer of 8.54 times 10 to the minus 5 meters per second. And then the last bit, very tricky. So why does the drift velocity stay the same? It's because the increased magnetic induction has caused more charges to be separated vertically across the plate, or more electrons gather at the bottom of the plate. And this in turn will increase the electric force or the electric field strength across the plate. Very tricky. Okay, let's have a look at another paper. We're going to have a look at the 2022 paper, and it's question 14, still on uniform fields. And again, have a go at the question first, and then come back once you're ready to see how we have done it. So in a cathode ray oscilloscope, electrons are accelerated from rest between the cathode and the anode, and the electrons then travel with a constant horizontal velocity between the parallel deflection plates, and this arrangement is shown in figure 14a. So there's the cathode at the left hand side of the apparatus and the anode. Now the charges will be accelerating between those two, and then they'll travel at a constant speed through the parallel deflection plates. And in part A, we're told the electrons pass through the anode with a horizontal velocity of 2.9 times 10 to 7 meters per second. And we have to determine the potential difference between the cathode and the anode. This is a higher physics question. And remember, you do still have the higher relationship sheet in your relationship sheet booklet. So, the work done on a charge moving through a potential difference is W equals QV, and the energy gained by the charge as it moves across that potential difference is a half mv squared. So QV equals a half mv squared. So if we rearrange that, then the potential difference between the cathode and the anode will be equal to half mv squared divided by Q. So V will be equal to 0.5 times the mass of the electron, which you'll get on your data sheet, that's 9.11 times 10 to the minus 31, times the velocity that we're given, 2.9 times 10 to the 7, and don't forget to square it, divided by the charge on the electron, which again you'll get on your data sheet, which is 1.6 times 10 to the minus 19. And that will give us a potential difference between the cathode and the anode of 2.4 times 10 to the 3 volts, or 2400 volts. 14b, on the diagram below, sketch the electric field pattern between the parallel deflection plates. Well, it's a uniform electric field, so we want straight, parallel lines the same distance apart. Use a ruler and make sure those lines are touching both the top and the bottom plate. And the direction of the field is the direction that a positive charge would experience a force, so that would be downwards. 1 mark there, and don't forget there's an additional diagram if you mess it up at the back of the booklet. And then in part C we've to explain why the electrons follow a curved path between the parallel deflection plates. Well, the top plate is positively charged and the bottom plate is negatively charged. And if we fire an electron in from the left hand side there, then it will be initially travelling with a constant velocity, but then when it enters the field, it's going to experience an electric force that will make it curve upwards. And this is a wee bit like an upside down projectile. Remember projectiles from higher physics? A projectile's got a constant horizontal velocity, but it's accelerating vertically. Well, it's the same here. The electrons will have a constant horizontal velocity, but they will have a vertical acceleration due to the force on them due to the electric field. And then part D, the potential difference across the parallel deflection plates is 0.90 kilovolts, and electrons passing between the plates are deflected by 4.0 millimeters in the vertical direction, and that's shown in figure 14b. And in part 1, the vertical component of the velocity of the electrons is 1.2 times 10 to the 7 meters per second as they exit the region between the plates. And we've to show that the vertical acceleration of the electrons between the parallel deflection plates is 1.8 times 10 to the 16 meters per second squared. Remember, this is an upside down projectile, so we can use our linear equations of motion here. And remember what we did for higher projectiles? We wrote down the 5 variables. It might be suvat or tuvas, and then you fill in the numbers that you know. So the initial vertical velocity of the electron was 0 as it entered the parallel plate region. The electrons were deflected with a vertical displacement of 4.0 millimeters. And the final velocity as the electrons exit the region between the plates, we're told that in the first line of part 1 of the question. The vertical component of the velocity of the electrons is 1.2 times 10 to the 7 meters per second as they exit the region between the plates. So V is 1.2 times 10 to the 7. And once you've got 3 numbers on that list there, you can work out the one that we're looking for, which in this case is the acceleration. So we go to our higher relationship sheet and we're going to use the relationship V squared is U squared plus 2AS. Then we're going to sub in everything we know. So the final vertical velocity was 1.2 times 10 to the 7. And don't forget to square that. And that's equal to the initial vertical velocity, which was 0 plus 2 times the acceleration times the vertical displacement, which we were given on the diagram of 4 times 10 to minus 3 meters or 4 millimeters. Now if we rearrange that for the acceleration, then A will be equal to 1.2 times 10 to the 7 squared divided by 2 times 4 times 10 to the minus 3. And if you do that correctly on your calculator, it'll give you an answer of 1.8 times 10 to the 16 meters per second squared, which is a huge acceleration, and it is a huge acceleration. Plus the fact this is a show question, so make sure you give your answer exactly the same as it's given in the question. Okay, Moving on, 14 part D, part 2, by considering the electric field between the plates, determine the vertical separation of the plates. So we want this relationship, and it's small d that we want to work out. Now, before we can work out small d, the vertical separation of the plates, we need to work out the electric field strength. And we've got another relationship for working out electric field strength. It's this one, E equals F over Q. And then we can make these two both equal to each other. So V over D equals F over Q, and then we rearrange for D. So D will be equal to QV over F, and we know what Q is, we know what V is, but we don't know F, we don't know what the electric force is. But wait a minute, we've just worked out the acceleration of a charge moving between those two plates. So we can use F equals ma to work out what that unbalanced force is. So let's sub in for F equals ma into this relationship, and we get D equals QV over ma. And now we're ready to substitute everything in. So Q is equal to 1.6 times 10 to minus 19 times the voltage, which we were given at the top of the question in the diagram. It was 0.9 times 10 to the 3. And that's divided by the mass of the electron, which is on your data sheet, 9.11 times 10 to minus 31, times the acceleration from the previous part of the question of 1.8 times 10 to the 16. And if you do that correctly on your calculator, you'll get 8.8 times 10 to the minus 3 metres, or 8.8 millimetres. Let's have a look at the marking instructions then for this whole question. So 14a was the higher physics question to work out the potential difference between the cathode and the anode. That was quite tricky because you had to use the work done equation and the kinetic energy equation, equate them, and then substitute in all the values in order to work out the potential difference. Part B was the uniform electric field pattern. Notice on the right hand side there it says the field lines must be straight and spaced uniformly, and the field lines must start and end on the plates. That's tricky. Then part C is our electron projectile path, because the electrons are travelling with a constant horizontal velocity, but they have a vertical acceleration due to the electric force. And notice on the right hand side there it says do not accept attracted to the top positive plate unless you make reference to the unbalanced force for the second mark. Then part D, this is our linear equations of motion from higher, to work out what that vertical acceleration is. You're only getting 2 marks here because it's a show question and you were given that final answer. And then D part 2, very tricky. There's no mark for F equals ma, but you do have to realise that you have to multiply the mass of the electron by the acceleration of the electron to get the unbalanced force acting on the charge by the electric field. You're then combining the two electric field relationships, F equals QE and E equals V over D, and then you are substituting in all the values for the third mark and the final mark for the final answer with the correct units. Very tricky question. We're including National 5 relationships, higher equations of motion, and multiple advanced higher physics relationships. Phew! Right, that's it for this one. Next time, we're going to have a look at circuits. So that might be capacitors, or inductors, or both. We'll see you in the next one.